Hi dear students, welcome to today's class. Today we discuss about the third type of two-component system, that is liquid-liquid system. Previously we have discussed about solid-liquid equilibria as well as solid-gas equilibria. We discussed first of all what are the types of liquid-liquid equilibria, in which we have a detailed discussion of one of the type, that is partially miscible liquid system, in this episode. Related to this discussion, we come across two important terms: lever rule as well as critical solution temperature. First of all, what are the types of liquid-liquid system or liquid-liquid equilibria? We are considering binary liquid system. That means system involving two liquids, which can be of three types. One is completely miscible or completely miscible liquid system. For example, if you mix water and ethanol, they are soluble to each other in all proportions, completely miscible. Regarding solubility of liquids, we consider a fundamental concept that is called like dissolves like. So water and ethanol is completely miscible, benzene and toluene is completely miscible, etc., which are also called solution because it is a homogeneous mixture, so it's a solution. The second type is partially miscible. Two liquids can be partially miscible. That means they are not completely soluble in all proportion. Example is water phenol system. If you add a little amount of phenol to water, it completely dissolves. But if you add more of phenol, then solubility will decrease or it will become insoluble. That is partially miscible. Water phenol system, water aniline system, hexane, nitrobenzene, etc. And the third type is completely immiscible liquids. Right? Immiscible. For example, if you add benzene to water, one is polar, the other is non-polar, and it will remain a separate layer. Even if you add only a little amount of benzene to water, it will not dissolve, completely immiscible. In this module of phase equilibria, we are discussing the second two types. The first one is solution, that is dealt in another module. In this class, we discuss the second one, that is partially miscible liquid system. Okay. Now, we have the example, that is phenol water system, partially miscible liquid system. So we have the phase diagram for this water phenol system here. As usual, temperature and composition is plotted. This is 100% water or 0% phenol, 100% phenol and 0% water, and it is a parabolic curve. We can draw various informations from this graph. It's very interesting example, that is water phenol system. Okay. Suppose you are taking a boiling tube, right, and you take some water in it, to which you add a little amount of phenol. To water you are adding a little amount of phenol, a few drops. What will happen? It will completely dissolve. See, water and phenol has some similarity, that both contain OH groups, so hydrogen bonding is possible. At the same time, it has benzene ring, which is aromatic group. So when you add more of phenol, a stage is reached when they become insoluble or they separate into two layers. So on adding more phenol, phenol being more dense will go down and it form a layer below. And it will remain as two layers. There will be a meniscus here. So this is the phenol layer and this is water layer. Right? This is the phenol layer and this is the water layer. But interestingly, it is not that this is only phenol and this is only water. No. It is that this lower phenol layer will contain sufficient amount of water in it, or it is a saturated solution of water in phenol. Consequently, this water layer also will contain sufficient amount of phenol in it, or it is a saturated solution of phenol in water. So this is lower layer water in phenol and this is phenol in water, and they are actually in equilibrium. A system at equilibrium will have certain properties which are constant. Here they will have same vapor pressure for the same temperature and pressure. Always we plot phase diagram for two component system at constant pressure. Say it is 1 atmosphere, and if you keep the temperature constant, then these two solutions will have the same composition that will remain irrespective of the amount of the liquids taken. Even if you mix any amount of phenol and water here, the two layers will have the same composition as long as temperature is kept constant. Now these kinds of solution where they are in equilibrium for a partially miscible liquid system, these two solutions are termed as conjugate solution. These are called conjugate solution, right? Which are in equilibrium. So this is the situation in phenol water system. Now let us go to the phase diagram and see what are the features, points which we can draw from phase diagram. Okay. See, let us take a point here. That means a low temperature, say room temperature, and this point corresponds to more of water and a very less amount of phenol, right? And as usual, in the phase diagram, the area within the curve, it will be two phase or F equal, you will have the degree of freedom here will be 1 because two phases. So when you apply phase rule, 2 plus 1 equal 1. It is monovariant here. Outside the curve, it is one phase. Homogeneous solution means the two liquids are soluble above this curve. So F equal to here, bivariant, right? Now let us take a point here, right? That means you have taken water and added some phenol and it is dissoluble. So it's a single phase. Now what happens? Now you are going along. You are moving along and you are entering this curve here. Suppose you are now here, this point. Here it is, say for example, 80% water and 20% phenol. So more phenol is added and you are inside the curve. So what is it? It will be a two phase. That means now the phenol and water will separate into two layers like this and form, as I said earlier, two layers, two conjugate solution. This one lower layer water in phenol and upper layer phenol in water, right? Suppose you are keeping temperature constant and adding more and more phenol. What happens if you add more and more phenol? The phenol layer will grow in size, water layer will become smaller and smaller. Actually, you will have to take a bigger test tube or a vessel to contain it because you are adding more amount of phenol. So what happens when you move along this, amount of phenol increases so much. That means you are moving along, this means you are going to 100% phenol. That means when more and more phenol is added, then amount of phenol increases and relatively amount of water is less, then that water will dissolve completely, and when you reach here, it again becomes homogeneous. Why? Because so much of phenol is there and a little amount of water will dissolve in it. Again you become single phase. So here it is one phase and two phase, and again you come out as one phase. So now it may look like this, something like this. It is full of phenol and water has dissolved in it. Initially it was like this, only water, then water and phenol layer is there, and then phenol dominates and it becomes larger proportion, and it again becomes single phase because the little amount of water has dissolved in it. Okay, now the next is about what is called lever rule. What is lever rules? Let us take a point here. For example, suppose you are here, a point here, okay? You are mixing this proportion. Say for example, 70% water and 30% phenol is mixed, and you draw a tie line here, right? You are drawing a tie line here. You will meet 2 points. See, I have told you already that when you have mixing reasonable amount of phenol added to water, it will separate into 2 layers and you will have conjugate solution, I said. So this is the water in phenol layer and this is water layer, right? Okay. Now, what is the composition of these 2 layers? This is phenol layer, that means water in phenol layer, and this is phenol in water layer. What is the composition of these 2? That is obtained from tie line. See this, you can see when you draw the tie line, you are meeting 2 points, 1 point here and 1 point here in the curve. Now this is the composition of which one? See, this side is major component is water. So this point represents the composition of water layer, and this point on the curve, if you go down, you get the composition of the phenol layer. You understand? So you get the composition of the 2 layers from this curve, right? So you get the composition here. If you keep temperature constant, even if you add any amount of phenol into it, composition of the 2 layers remain constant. That is a property of conjugate solution which are in equilibrium. Now what is lever rule? Lever rule gives the relative amount of the 2 layers. What is the relative amount of the 2? That is obtained from lever rule. Actually lever rule is coming from physics. It is related to law of moment, you know. Suppose you have a fulcrum here and 2 weights are here like this, right? This is a heavier one. Suppose W, this is W1, this is W2, suppose, and this is X1 and X2 is the distance from fulcrum. You have this relation according to law of moment, W1 X1 is equal to W2 X2, or W1 by W2 is equal to what? X2 by X1. That means this W1, this weight is proportional to this distance, right? And vice versa. Similar to this concept, we can we consider in phase diagrams, not only in this, any phase diagrams, what we have finished like the simple irradiated system also, we can apply lever rule. So according to lever rule, it says that the relative amount of the 2 phases, the 2 layers is obtained as amount of, suppose we note this is L1, layer 1, and this is layer 2, suppose amount of L1 by amount of L2 is equal to what? Amount of this is proportional to this length. As we are here, this is the point we have taken, the composition we have taken, Suppose this is marked as X, okay? So amount of this layer is proportional to this distance, that is L2X, by amount of this layer, phenol layer, is proportional to this distance, that is L1X. This is lever rule, right? So ratio of the amount of the two layers is given by this ratio, this distance ratio. So amount of the water layer, that is phenol in water layer, is proportional to this one. It is sensible, understandable, because it is more of water, right? So it is proportional to larger distance. Amount of phenol is less, right? For this particular composition, say for example it is 70% water, 30% phenol. So you have less amount of phenol. So amount of phenol layer is proportional to this smaller distance. Correct? So this is lever rule. You can apply lever rule to even simple eutectic system also. For example, if you take the phase diagram of simple eutectic system, you know, it is like this, for example, and this is A, this is B, this is eutectic composition C, eutectic point. If you cool down a melt, you know, suppose you are, a solid A separates out in equilibrium with the liquid melt. Suppose you are somewhere here for this temperature. So suppose you are here, you draw a tie line, correct? And you get 2 points. This point, that is solid A. This point, the composition of the remaining liquid melt. So the ratio of these two is given by these two distance. For example, suppose this is marked as A, this is C, or let us write B here. This is X. So amount of A proportional to this distance, amount of B proportional to this distance, right? When you go down, you can see this distance is increasing. What does it indicate? Distance is increasing means more and more A is coming out, correct? So this lever rule is applicable to any phase diagram. Okay. Now finally, what is the influence of temperature on this phase diagram? Again, suppose let us take a point here. Okay, let us take a point here. Let us mix water and phenol for this composition. Say for example 60-40, like that. Okay, you have the two layers, phenol and water layer. On increasing temperatures, if we have already seen that, or you take the same point only, the same thing. We have already seen that these are the two compositions of the two layers. What happens when you are moving along? When you go up? When you go up at a higher temperature, you can see when you draw the tie line, you can see the composition or the solubility increases. That means it is moving this side. Actually, this graph is made up of two curves, a parabolic curve. One is going like this and the other is going like this. What does it mean? When you rise temperature, for the water layer, its solubility increases because it's moving this side. For phenol layer also, when you increase temperature, it is moving this side, means it is become richer in water, solubility increases. Or in other words, when you increase temperature, solubility of both phenol layer and water layer increases. Like this, it goes like this, it comes closer, right? And what happens? At a point, it becomes equal or it becomes a homogeneous liquid. So there is a temperature at which the two liquids become homogeneous. We know that when temperature increases, solubility increases. So solubility of both the layers increases and finally they become a homogeneous liquid. So you get out of the curve. So if it is here, you are going like this and then you come out of the curve, it becomes homogeneous. Anyway, if you take here this particular composition, you have two layers with two compositions. You go up, solubility increases, and when you touch here, it becomes a single layer. For this curve, there is a peak that is called by critical solution temperature. This is a peak of the curve. See, above the importance of this temperature is that above this temperature, for any composition, these two liquids will give only one solution, or critical solution temperature. It is otherwise called consolute temperature, abbreviated as CST. It is defined as the temperature at which two partially miscible liquid systems become completely miscible. It's a temperature below which the two liquids, partially liquid system will remain in two phase, above which it become one phase. You can state in different words. So the temperature at which and above which two partially miscible liquids become completely miscible and become a single phase or become homogeneous, it is called critical solution temperature. For phenol water system, the temperature is 60 degrees Celsius. For any temperature below this, you have a tie line, you have two layers, two phases with different composition. A composition corresponding to this CST is found to be 34% of phenol, right? So CST is an important property of partially miscible liquid systems. Actually, phenol water system and the CST is coming in your physical chemistry practicals. So this theory is important. You should understand this theory very clearly, right? So this is phenol water system having a critical temperature, and this particular critical temperature is called upper critical temperature, or we write TUC, because you are getting a temperature above upper critical temperature. That means the two liquids become soluble when you increase the temperature. But there are some interesting cases where two liquids solubility increases on decreasing temperature. For example, it is triethylamine water system. Triethylamine water system. For this system, the phase diagram is like this. See, it's just reverse. It is like this, right? It goes like this, and that means the two liquids, solubility of the two liquids increases on lowering the temperature, and you get the CST down. It is found to be 18.5 degree for this system, 18.5 degrees Celsius. There are some reasons like a tendency to form some complexes. That's why solubility is enhanced by lowering the temperature, and corresponding composition triethylamine water system is 18.5. Interestingly, there are some systems which has got, this is known as lower CST. So CST is of two types: upper CST like in phenol water system, lower CST like triethylamine water system. And in the case of another system, that is nicotine water system. Nicotine, you know, it's a liquid. Nicotine, which is obtained from, it's an alkaloid obtained from tobacco leaves. It's a liquid, and these are all amines. These are all nitrogen-containing alkaloids. So this nicotine water system is having a phase diagram like this, which has like something like this, which has got both upper CST and lower CST. So there is a point here above which it is homogeneous. There is a temperature here below which also it is homogeneous, right? Okay, the temperature is found to be 61 degrees Celsius is the lower CST, and upper CST is 208 degrees Celsius. For a composition of, it is 34% corresponding composition. Anyway, in the case of nicotine water system, it has both upper and lower CST. For this one, it is having lower CST. For phenol water system, it has upper CST. So that's about this partially miscible liquid system and the phase diagram of these systems. we have the last part of this module, that is immiscible liquid system, that in the next class. Till then, bye.